suppose that we have a linear time-invariant system with impulse response h of n and input signal x of n that is equal to 0.5 if n is 0 and 2 if n is 1. Okay? So basically, this x of n, right, can be written as a superposition of two unit impulses, one at time 0 and one at time 1. Right? So this is 0.5 times delta n plus 2 times delta of n minus 1. So x of n is the superposition of two unit impulses. Now suppose that, h of n looks something like this. Okay? So if you recall what is h of n is the unit impulse response, meaning that it is the response to a impulse inserted at time 0. Okay? So the output, right, since the input is the superposition of these two unit impulses, the output should then be the same superposition, right, with the same coefficients of the corresponding impulse responses, which is hn and h of n minus 1. Okay? All right, so because hn looks like this, right, so 0.5 hn will look something like this. Okay, so so suppose that this is 0.5, right? So we have 0.5, 0.5, 0.5, 0. So on and so forth. Okay. Plus 2 times h of n minus 1. So, right. So h of n minus 1 is basically this h of n shifted to time 1, right? So I should have values at time 1, 2, and 3. And the values are multiplied by 2, right? So this is 1, this is 2. I should have values like this. So on. Okay, so this is 2. All right. So yn is just the summation of these two. So if you plot this out, you should have a 0.5 here. You should have 2 plus 0.5 here. So you should have 2.5, 2.5, 2, and 0 everywhere else. Oh, sorry. Okay. All right. So any questions about this example? So here we're essentially viewing the output of a system as the superposition of these time-shifted impulse responses. Okay. So here we viewed yn as a superposition of these time-shifted impulse responses, for all time shifts. Okay. Now we can also view this in a slightly, different way. Okay, so instead of viewing yn as a superposition of these time-shifted impulse responses, we can also view yn. We can also view yn, right, for a particular time instant n as a weighted sum of the contributions of the input signal at over different time instants. Okay, so the output at time n can also be viewed as a weighted sum, right? The sum of the contributions of x at different time instants, okay, weighted by this h of n minus k. Right? So we're viewing y, the output at time n, as the sum of the contribution of x contribution of, let's say, input at time k. Okay, and the weight that we give for the input at time k would change according to this h of n minus k. Okay. Now, if you look at this h of n minus k, h of n minus k is actually a time reversed, right? If you're viewing k as a time index here, h of n minus k is actually a time reversed and shifted version of h. Okay, so it's time reversed and shifted to time n. Okay. So this thing here, right, when you're viewing it with respect to k, okay, can be viewed as a time reversed and shifted version of hk. Okay, and the shift is to time n. Right, so this is shifted by time n. Okay. Now, suppose that we follow this example on the previous slide, right? Suppose hn is this sequence here where you have ones at time 0, 1, and 2, and 0 everywhere else, right? So this is sort of like a rectangular sequence. Okay. So if hn looks like this, then h of n minus k, suppose that hk is this, then h of n minus k would then be this rectangular function, time reversed and shifted to time n. Okay. So if you just time reverse it, right, then this h of 0 minus k, right, which is the just time reversed version, will have ones at -2, -1, and 0, and 0 everywhere else. Okay. Now, depending on the value of n, right, these values will be shifted. The origin will be shifted to n, right? So if n is 1, then you can see that this pulse here is shifted to time 1. If n is 2, then this origin is shifted to time 2, and so on and so forth. Okay? So this h of n minus k, right, the function you see here is the weight that we impose on the corresponding values of x in this summation here. Okay. So for example, if you want to look at the output at time 0, I suppose you want to look at the output at time 0, then by the above formula, this is xk h of 0 minus k, k from minus infinity to infinity. Okay. So you're summing the contributions of xk, each value weighted by the corresponding value in this time-shifted impulse response h. Okay. So here you see that 0.5 is multiplied with 1, 2 is multiplied with 0, and then when you sum them up, you will just have 0.5. Okay. Now, when you're looking at different time instants, right? When you're looking at the output at different time instants, the values of the input should be weighted differently, right? Because this h of n minus k would look differently. Right? So, for example, if you're changing a time instant to n equal to 1, in this case, xk should be weighted by h of 1 minus k. Okay. And h of 1 minus k is this sequence here. Okay. So this is saying that in this case, right, to find y1, we should weight 0.5 by 1, and weight 2 also by 1, and 0 everywhere else. Okay. So we should have 0.5 plus 2, which is 2.5. Okay. So we can do one more, right? So suppose that we have, let's say, a y of 2. In this case, hk is weighted by h of 2 minus k, k from minus infinity to infinity. Okay. So h of 2 minus k is this sequence here. Okay. So here, 0.5 is weighted by 1, 2 is weighted also by 1, and then 0 everywhere else. Okay. So again, we have 0.5 plus 2, which is again 2.5. Okay. So you can continue to do this for y at different time instants as well. Right. And you can double check with our result on the previous slide. Right. So here, y0 is 0.5, y1 and y2 are both 2.5. So if you check with the result before, right, indeed, at time 0, the output is 0.5. At time 1 and 2, the output is 2.5. Okay. Right. Okay, so any questions here? Do we have any questions? 李子怡在吗？
在。
有没有什么问题？
没有。
都可以了解吗？所以你大概可以了解说前一页就说讲的观点跟这一页对于这个 YN 的观点是有怎么样的不同吗？
怎么样的不同？有什么不同？ 前一个是哪里？是这个吗？是这个吗？它是指这个。
好，没有关系。那就是主要的差别就是说，在前一页这边就是在前一页这边，我们的 output y 就是我们把整个 output y 的这个 sequence， 我们看待成很多不同的这些time shifted impulse response 的叠加，所以就是好像很多不同的这些 time shifted impulse response， 我把它叠加起来，就会变成这个 yn。OK， 所以这是一种看法，对，这是一个观点，对。那同样的式子 ，right， 其实我们可以从另外一个观点来看，就是说从另外一个观点呢，我们其实可以把 yn， 就是说在时间 n 的 output 看待成是我的 input signal， OK 的一个就是看待成就是说我的 input signal 的一个综合在时间 n 的 contribution，OK， 就是我在某一个时间点的 output 是我的整个 input signal 综合起来的一个效应。那怎么样综合起来就会 depend on 我要乘上怎么样的一个 weight h of n minus k。OK， 所以我如果看不同时间点的 output， 我就必须要去 weight 我的 input by different coefficients h of n minus k. Okay, so this is basically just two different ways of viewing this convolutional operation. Okay. Okay. And the weights that we impose on the input signal are basically time reversed and shifted versions of the impulse response h of k. Okay. So if you're looking at different the output at different time instants, then this impulse is shifted to different positions. Okay. All right. Now let's look at another example. Okay. So here, suppose that our input xn is this geometric series on the positive axis. So this is alpha n times the unit step u of n. Okay. So this is non-zero only when n is greater or equal to 0. So suppose we look at the case where alpha is between 0 and 1, so that as n increases, this value decays. Okay. All right, so here we have a illustration of x, right? So you see that there are only non-zero values on the non-negative axis, and that it decays as k increases. Okay. Now this input is inserted into a linear time-invariant system with impulse response h of n that is equal to this unit step function un. Right, so h of n looks something like this. Okay. All right. Now, to obtain y of n, right? To obtain y of n, we should sum the contribution of the input weighted by the time reversed and shifted version of the impulse response. Okay. So a unit impulse, if you time reverse it, now has values only in the negative axis, right? And it's shifted, the origin is shifted to time n, okay? So if you simply time reverse it, h of minus k would look something like this, okay? But if you shift it to different time instants, let's say time instant -1, you get something that is 1 up to -1, right? The origin is moved up to -1. Or if you pick n equal to 1, then the origin is moved to the time 1, and so on and so forth, right? So if you move it to some n that is greater than 0, then h of n minus k would look something like this, right? So you have a 1 all the way up to time n, right? And if you have n less than 0, then you would look something like this. Okay. So depending on what value of n you're looking at, you want to weight the values of x with a different, time-shifted versions of h of minus k. Okay. Now you can see that, if n is less than 0, right? For example, if you're looking at n that is -1, then xk and h of n minus k has no overlap with each other. Okay. So the pointwise product of this xk and h of n minus k, if n is negative, would be 0. Okay. So for n less than 0, we can see that xk times h of n minus k is 0 for all k. Okay. So therefore, if you sum this up, right, yn will certainly be 0. Right. Now, on the other hand, if n is greater or equal to 0, okay, so if n is greater or equal to 0, something like this, right, when you multiply this with xk, you will see that you basically capture the values of xk from time 0 up to time n. Okay, so xk times h of n minus k for n that is greater or equal to 0 is captures the value of xk, which is alpha to the power k, for k from 0 up to n, okay, and 0 otherwise. Okay, so in this case, right, yn, which is the summation of alpha k from 0 to n, right, we're summing up these values, alpha k, for k from 0 up to n, right, this is equal to 1 minus alpha n plus 1 over 1 minus alpha, right? So this is the formula for the sum of a geometric series. Okay. So in summary, right, from the above, we're saying that yn, right, should be 0 for n less than 0, and should be 1 minus alpha n plus 1 over 1 minus alpha for n greater or equal to 0. Okay. Or we can express this more conveniently using the unit step function, right, where we can just write this as 1 minus alpha n plus 1 over 1 minus alpha times the unit step function, which is, indeed 0 for n less than 0 and 1 for n greater or equal to 0. Okay. And this is, this is the plot of this output y of n that we derived. So any questions here? Okay. So if not, let's do one more example. Okay. So when we are working on these few examples here, right, you can sort of observe one thing, right? So when you're trying to compute this summation of xk h of n minus k for different values of n, we're basically multiplying this xk with different time shifted versions of the time reverse of h of k. Okay. And this time shift shifts h of minus k to time n, right? So as n increases, this is like taking h of minus k, right, and sliding it across this x of k. Okay. So this is what this next example is trying to help you visualize, right? So when we take the convolution between xn and the this impulse response h of n, this is like taking this time reversed version of h of n and sliding it across x of n, okay, as the output time instant you're looking at increases. Okay. So here, suppose that our input signal x is just this rectangular signal that is 1 from 0 to 4, okay, and 0 otherwise. So it looks something like this. And our h of n is this, increasing sequence alpha n for n from 0 up to 6. So it looks something like this, right? So it's 0 outside of this time window. Okay. Now, when you take the convolution between these two, right? You take hn, you time reverse it, and then shift it to time n. Okay. So if n is less than 0, then your time shifted version would look something like this. Okay. So it takes this h of n here, it flips it around, okay, and then shifts to the time n, which is negative in this case. Okay. Now you can see that as long as n is less than 0, there will be no overlap between this time shifted impulse response and the signal x. So when you multiply them together pointwise and sum them up, the output yn will certainly be 0. Okay. So this is true, right? As long as n is less than 0, even as you slide closer to 0. But then, as you approach 0, right? When n becomes 0, you start to have one overlap. Okay, you start to overlap with this signal x. Okay. So as n goes, from negative up to the region of 0 up to 4, you'll start to see this overlap with the signal xk. Okay. And in this case, right, when n is between 0 and 4, then this right edge of h of n minus k, right, this is this is h of n minus k here, right? The right edge of n minus k, h of n minus k will, still be within the range of x. So xk times h of n minus k will be equal to alpha to the power n minus k, for k between 0 and n, and 0 otherwise. Okay? And if you sum them up, yn, okay, will be equal to summation alpha n minus k, k from 0 to n. And this will be 1 minus alpha to the power n plus 1 over 1 minus alpha. Okay? Now, if you continue to increase n, right, suppose you increase to the case where n is between 4 and 6. Okay? In this case, h of n minus k will completely cover the signal x of k. So in this case, hk, h of n minus k, is alpha n minus k, for k from 0 all the way up to 4, okay, because it completely covers the signal, okay, right? So then yn, right, is just a summation of these signals, right? So without going through the details, this is, which I believe you can work out yourself, right? This is equal to alpha n minus 4 minus alpha n plus 1 over 1 minus alpha. Okay. Now, as you continue to increase n, right, as you continue to increase n, this h of n minus k will continue to slide over, right? But now it will only, cover only the tail part of h of n minus k will overlap with x, right? So if n is in this range, then only the tail part of h of n minus k will be overlapping with x of k. And in this case, xk h of n minus k will have a range from n minus 6 to 4 and 0 otherwise. And similarly, if you sum this up, you would get yn, that is alpha n minus 4 minus alpha to the power 7 over 1 minus alpha. Okay. Now, finally, if you increase n beyond 10, right, if n is greater than 10, then, they again will not overlap with each other. In this case, xk times h of n minus k will be 0 for all k, and therefore, yn is just 0. Okay. Okay. So in this example, we can see that, when you're trying to find this output yn, by taking the convolution between xk and h, by taking this weighted sum of xk weighted by this h of n minus k, okay, from minus infinity to infinity, right? This is like sliding a time reversed version of the channel in response through x, through the input signal x, okay? And depending on, how much they overlap, right? Depending on the relative position of x and this sliding h of n minus k, your output signal may behave differently, right? So for n less than 0, your output signal is 0. For n that is between 0 and 4, in which case only the front part of h of n minus k overlaps, you will have yn equal to this. For n, for n between 4 and 6, right? The two signals overlap completely, and yn will be equal to this. For n from 6 to 10, right? Only the tail part of h of n minus k overlaps, and this is what you get. And then for n greater than 10, the two signals start to leave each other, having no overlap, and therefore the output becomes 0 again. Okay. So if you collect all these results, right, this is the summary of the output signal that you would get. Okay. So they have, different behaviors in different time intervals, right? So this is n less than 0, right, from 0 to 4. From greater than 4 to 6, greater than 6 to 10, and 0 again. Now here, up to this point, we have only focused on discrete time signals, okay? Now we want to be able to extend the same concept to continuous time signals as well, right? So to do that, let us start out by,